Exercise 6C, solving trigonometric equations. Today's learning intention is about solving trigonometric equations, and the success criteria. What you need to be able to do in order to solve those trig equations is to determine the quadrants that the graph is going to go through, find the base angle, apply this to the domain, and then transform as required. So there's a couple of steps when solving trigonometric equations, and these are the things that we need to determine. So the first thing is we want to find out what is our base angle. So the first quadrant angle, irrespective of the sign. So I'll call this the base angle. Then, depending on the sign, it's going to be possible to be in two quadrants. So if our base angle is, say, pi on 3, and it's positive, well, that could, if we're looking at signs, positive in quadrant 1 and 2. So the next one that you want to look at is which quadrant is it in. And then finally, what you want to do is you want to be able to solve it based on our rules of symmetry. So we have our rules. This is theta, pi minus theta, pi plus theta, and 2 pi minus theta. So based on these particular rules, we can then go ahead and find all of the other angles. If we need more solutions for the domain, so if it's between 0 and 4 pi, for example, what you'll do is you'll just add or subtract the period to the two solutions as many times as you need. So noting the solutions after each addition or subtraction. There's going to be a little bit of a point before we do this. If you haven't translated or you haven't transformed yet the period, what you do is you just add and subtract 2 pi. But if you've already divided, then you will do the period. But I'll show you exactly what I mean when we actually do an example. Stop when all solutions within a specified domain are found. So I know that sounds confusing. Let's go ahead and actually try out the questions. So example 8, find the solutions to the equation sine x is equal to 1 on root 2. First, we're just going to look at this graphically, and then we're going to go ahead and do it algebraically. So the idea is that here is the graph of sine x, and equal to 1 on root 2. Well, here's 1 on root 2. What we can see is that we've got 4 solutions. And you can hopefully also see that those solutions are in the first two quadrants, so quadrant 1 and 2. Once I've found these, all I have to do is subtract, well, rather this one's going to go here, subtract 2 pi to get to my previous cycle. So that's at its essence what we need to be able to do. So let's go ahead and do this algebraically. Find the solutions to these equations. So as we said, the first step is to find the base angle. So I have sine x equal to 1 on root 2. If there's a negative, you can just ignore it, but x will be equal to sine inverse of 1 on root 2. So what I'm thinking here is sine of what gives me 1 on root 2. And if you consult your exact values table, that'll be pi on 4. The next thing I can see is that 1 on root 2 is positive. So in which quadrant is sine positive in? Well, that's in quadrant 1 and in quadrant 2. So quadrant 1 rule is theta, and quadrant 2 is pi minus theta. So then for 3, all we have to do is go ahead and apply this idea. So in quadrant 1, the angle will be pi on 4, and then quadrant 2, it'll be pi minus pi on 4. So that'll be 3 pi on 4. So these are the values of x. This is what it's going to equal. Now the domain is only between 0 to 2 pi in this case. So between pi and 4 and, the two angles will be pi on 4 and 3 pi on 4. So if we go back, we could even label them here. This is pi on 4, and this is 3 pi on 4. And if I wanted to find these two, because in this case the domain is negative 2 pi to 2 pi, it's very straightforward. All I have to do is subtract 2 pi from each of these. 2 pi is the same as saying 8 pi on 4. So 1 pi on 4 minus 8 pi on 4 is going to be 7 pi on 4. And then 3 pi on 4 minus 2 pi, so minus 8 pi on 4, is going to be negative 5 pi on 4. Sorry, this should be a negative as well. So it's as simple as that. Now, obviously, it does get a little bit more complicated if there are translations and so on, but we'll work that out as we get to it. Example 9, solve the equation sine theta is equal to negative root 3 on 2, and this time the domain is a little bit different as well. So as I mentioned in the previous video, between 0 and 2 pi, or if you have a distance of 2 pi, you can expect as many solutions as there are the number in it. So if that's a number 1, I will expect 1 round of solutions, which would be 2, because for every graph, there are 2 solutions. But of course, depending on what quadrants it is, it might be a little bit different. If I were to think about the sine graph, so negative root 3 on 2, and it's only between negative pi and pi, so that means I can get rid of this here. you can see I'm going to expect two negative solutions. So sometimes it does help to graph to be able to see that. But that's what I meant, that because that's one, I'm expecting one cycle, and for every cycle, there are two solutions. So let's go ahead and apply what we learned before. The first one is our base angle. Now for our base angle, I'm going to take the sign over to the other side, and I'm going to ignore the negative for now. So sine of what gives me root 3 on 2? Well, that's going to be pi on 3. So that's my base angle. The next thing is I'm going to consider the quadrants that it's in. So where is sine negative? Well, that's quadrant 3 and quadrant 4. Quadrant 3 is pi plus theta, and quadrant 4 is 2 pi minus theta. So I'm going to go ahead and apply my base angle to this. That's for part 3. So that's pi plus pi on 3 and 2 pi minus pi on 3. So that's going to be 4 pi on 3, and then this is going to be 5 pi on 3. Now, of course, what we can see is that both of these are outside our domain, because what I've actually done is I found the solutions here, but they're not the solutions I want. I want the solutions that exist one period before. So we now introduce our fourth step where I have to take away the period to be able to get to those solutions. So I'll have 4 pi on 3 minus 2 pi and 5 pi on 3 minus 2 pi. Keeping that in mind, that on 3, so 2 pi in regards to 3, that's 6 pi on 3. So what I'm thinking here is 4 pi minus 6 pi, that'll be negative 2 pi on 3, and 5 pi minus 6 pi is going to be negative pi on 3. And those are my two solutions here. So this will be negative 2 pi on 3, and this would be negative pi on 3. Example 10. Calculate the sum of the solutions between 0 and 2 pi for this particular equation. Now, when we have sine equal to cos, there's actually a very interesting thing that you have to do here, and that would be simply to divide both sides by cos. Now, why on earth would we do that? Well, sine divided by cos actually gives me a different trigonometric ratio, which is tan. So if I go ahead and do this, sine divided by cos is tan, and cos divided by cos is 1. So now you can see I've actually come up with a new equation. Now, I want my domain is between 0 and 2 pi. And this time we have a 3. So between 0 and 2 pi, I'm expecting 3 cycles, which means I'm expecting 6 solutions because it's double. Now, what you can do, you're not changing the domain, but what you can do just to know what domain you need to use is actually just multiply, just for your own working out, both of these by 3. So that means you need to find solutions by 0 to 6 pi, and what you'll notice is we're going to get to a point where we have to divide everything by 3 to get to x. When I divide by 3, then I'll get back to my normal domain. So this kind of helps you to find the right number of solutions if you multiply it by this dilation factor, and then we'll divide, which gets us back to our original value. All right, let's go ahead with our steps. So the first one is our base angle. So 3x, well rather, I'm just going to use theta. Theta is equal to tan inverse of 1. So tan of something equals 1, that's going to be pi on 4. So that's my first one there. The next one is, that 1 is positive. So which quadrants am I in? Well, tan is positive in quadrants 1 and in quadrant 3. Then what are the formulas for that? Well, quadrant 1 is just theta, and quadrant 3 is pi plus theta. So what I can do is go ahead and sub in pi on 4 now. That'll be pi on 4, and then pi plus pi on 4 is going to be pi plus pi on 4. So that's 4 pi on 4 plus pi on 4. That will be 5 pi on 4. So those will be my two angles. Now, what you'll think about is that this is what 3x is equal to. It's very important that you remember this is what this is equal to. If I go ahead and divide everything by 3, you'll notice that that's pi on 12 and 5 pi on 12, which are so small, and there are a lot more solutions that exist, which is why we have to continue so that we can fill out this 0 to 6 pi. So that's why we do that to help you out. Now, because I haven't yet divided by 3, we're not going to add on the period. If you divide by 3, then you can add the period, but I haven't divided by it yet. So what I'm going to do is I'm just going to add 2 pi to these. So your general rule is to just add 2 pi until you divide by the period. So I'm just going to continue on. This is for step 4 where we're finding more solutions. So 3x is equal to, so I've got 4 pi, pi on 4, 5 pi on 4. Now I'm going to add 2 pi to each of these, remembering in terms of on 4, 2 pi is equal to 8 pi on 4. So here is just 1. 1 plus 8 is 9 pi on 4, and 5 plus 8 is 13 pi on 4. And I still need to go 2 more. So remember, I need 3 cycles. So I'm going to just add 2 pi again here. So 9 plus 8 is 17 pi on 4, and 13 plus 8 is going to be 21 pi on 4. Now, I know these numbers seem really large, but all I need to now do is divide everything by 3. So I'll get x is equal to pi on 12, 5 pi on 12, 9 pi on 12, 13 pi on 12, 17 pi on 12, 21 pi on 12. And what you'll notice is that we have remained within our domain. So the other way you can do it, of course, is if you already divide by 3, here, then you would just add on whatever the period is. But I feel like this is just an easy way so that you always do the exact same thing. Leave the transformations till last, add on 2 pi if you ever want to go to a next cycle, and then divide right at the end. And that's it for this exercise.